And here we go with section 2.6, combinations of functions and composite functions. So yeah, I had to shorten the title. It says combinations of and composite functions, but it's combinations of functions and composite functions. So we have two separate topics. With, of course, me, Mr. Hain. So combinations of functions. So combinations of functions are super simple. The most complicated part is domain. Domain is just the possible values of x. What can x be? And this fancy symbol here just means intersection. So only the elements that are common to both domain of f and domain of g, where they overlap. I've got some examples coming. This might not look easy, but it actually is straightforward when you see it in action. So what are combinations of functions? What combinations of functions are? Bad English, I guess I'm Yoda. All right, here we go. A sum is just adding them together. A difference is just subtracting. You can remember the simple vocabulary difference means subtract. Product, of course, means multiply. So f times g of x is just f of x times g of x. And the quotient is f of f over g, or f divided by g of x. And here we see the quotient written out. And the special part here, since it's a fraction, we know the denominator cannot be equal to 0. Excellent. So what the heck do I mean? So I'm always going to give you, for combinations, I'm going to give you the function f of x, and I'm going to give you the function g of x. So whatever those two functions might be named, a, b, c, d, e, f, I don't know. But I'm going to give them to you. So let's look at a sum of these two functions. So a sum of these two functions is just adding these two together. So x minus 5, which is the f of x, and x squared minus 1, which is the g of x. So the most important thing here is you see I group together the second one because sometimes I have to distribute the operation. Since I'm just adding, there's nothing I have to change for the signs for x squared minus 1. So I take that away, and then I just put them in descending orders of x. So the f of x is just, f plus g of x, rather, is x squared plus x minus 6. That's it. Not asking you to factor, not asking you to do anything else. That's simply it. So let's look at what a difference would be. And again, the most important part is seeing that I've put the difference, so I'm subtracting the entire function g of x, which is x squared minus 1. This is important. This is where all the mistakes happen when people do this at the beginning. You see that it is x squared minus 1, but this negative sign makes the positive x squared negative x squared. This subtraction, because we're taking the difference, also makes the negative one here, the minus 1 in the quantity. Negative times a negative makes a positive 1 here. So that becomes negative x squared or minus x squared plus 1. It's changing the sign. So when I reorder those in descending powers of x, which is the proper way to write that function, I have f minus g of x is negative x squared plus x minus 4. All right, again, the most important thing here is to group when I'm adding and subtracting, especially subtracting. Continuing on, I'm going to multiply those two together. These are the same functions that from the previous slide. So I multiply x minus 5 times x squared minus 1, and we just FOIL. So x times x squared is x cubed. Negative 5 times x squared is minus 5x squared. X times negative 1 is negative x, and negative 5 times negative 1 is positive 5. Order of descending powers of x, and there you go. So let's look at a quotient. If I'm looking at a quotient, I just divide them, so I put g of x in the denominator. And now here, this arrow reminds me that whenever I have a fraction, I have to know where the denominator cannot equal 0. So I actually say where x squared minus 1 equals 0 to solve for this. Move the 1 to the other side and take the square root. So remember the square root rule. The square root of 1 is positive or negative 1. Two negatives make a positive 1. So that makes the denominator equal to 0, positive or negative 1. So x cannot equal positive or negative 1. So those are exclusions from the domain of f over g. So let's take a closer look at domain by using square root functions. And remember, the square root property must be greater than 0 for non-imaginary answers. Like I can take the square root of a negative, but like the square root of a negative gives me I pop my I out, if you remember my previous lecture. And that is how we deal with negative roots. So if we want real numbers, which is for the domain, it has to be non-negative, so greater than or equal to 0. So here you see I've taken the domain of f, I just take what's under the square root only and set it greater than or equal to 0. And I add each side, so I have domain of f is greater than or equal to 3. Now for the g of x, I set the same thing. I take the same part and I make it greater than or equal to 0. I move the positive 1 to the other side, and I have the domain of g is greater than or equal to -1. Now I was adding these functions together, so that's how I get f plus g of x, so I have them too. I can't do anything, there's nothing to simplify, so I need to find the domain. So what I'm going to do, remembering that the square root must be greater than 0, so I'm going to use these two pieces of information. I'm going to mock up a number line, so I've got -1 and I've got +3. So I'm going to graph the domain of g is greater than -1, so it goes this way, and the domain of f is greater than 3, so it goes this way. Now remember I told you that the intersection symbol, this upside down U, means where they overlap. And this is what I mean. Visually, they start overlapping right here at greater than or equal to 3. So that's why the domain for f plus g is x greater than or equal to 3. Deep stuff. Overlap. That's the union, intersection. So let's take a look at some composite functions. Now this is the second subject of this exploration. So f composed with g is denoted or shown by this. Now that it's not if it's not in g, the domain of the f is f composed with g. If it's not g of x, if it's not in the g of x, if it's not in the domain of the g function, it's not in the domain of the overall composition. And here, this just means I'm taking the f of x and I'm making it the f of the g of x. It sounds super confusing. And that's not a little o. It's actually just a little open circle. And the value of the answer of g of x is one way of thinking of the composed function. All right, this sounds crazy. So let's take a look at an example. So I'm going to give you f and g for these functions. So I'm going to take a look. First, in checkpoint 4a, I'm composing these two functions together. So my f of x is 5x plus 6. Now it says f of the g of x, so my g of x is this here, 2x squared minus x minus 1. That actually gets plugged in and substituted for this x. And that's my composed function before I simplify. I'm just going to distribute and combine like terms. So I have my f of the g of x is 10x squared minus 5x plus 1. All right, so it's actually a lot simpler when you see it. The f composed with g, or the f of the g of x, means everywhere that I see an x in f, right here, I'm going to plug in the entire g function and then simplify. So what does it look when I go the other way? Okay, it's going to be a little bit more complicated because you see I have an x squared and an x here, so I'm substituting in twice. So I'm going to start by writing my g of x, and then everywhere I see an x, I'm going to replace it with my entire f function. So you see I've replaced it here by putting in 5x plus 6, and I've replaced it here again by putting 5x plus 6. Now this is squared because this x was squared as well. So I'm going to FOIL out here and distribute the negative. So it's negative 5x, and then since this is a positive 6, it becomes minus 6, minus 1. It tags along. This minus 1 is the same minus 1 that's been hanging out at the end. And here I just FOILed, so I didn't show the work for the foiling, but you can do this on the side of your notes if you want. And here I'm just distributing the 2. And I'm going to combine like terms. And that's how I get 115x, because I have this minus 5x, so 120 minus 5x is 115. And 72 minus 6 minus 1 is 65. G composed with f of x, or g of f of x. Yeah, some people say Goff and Fog, and I might say it in other videos, but it's just a colloquial term. Again, remember, that's not an O, it's a little dot. Open dot. All right. Sweet. So now we got to find the value of a composite function. Now, there's not an example in your book. I just called this checkpoint C of checkpoint 4, but it's not really in your book at all. So I'm just going to go through this. Again, remember, if I'm finding the fog of 1 or the f of the g of 1, I'm actually just finding the value of g of 1. So remember, g was just 2x squared minus 1 minus x minus 1. So I substituted 1 in for g. And of course, this just becomes 0. So I take that value of 0, and I'm going to plug it into my f function. So the f of 0, if it was 5x minus, or plus 6 rather, that 0 just gets substituted in for the x. So 5 times 0 is 0, 0 plus 6 is 6. So the f of 0 is just 6. So since I took the function, the value of the f function at the answer of what the g of 1 is, it's the simple way of just saying the f composed with g of 1 is the number 6. Yeah, I kind of wrote the number 6 kind of funny, but it is 6 because that was the value of f and the answer of g of 1. I'm going to look at this again later. So let's take a look at rational composite functions. So for rational composite functions, I have fractions. Rational just means fraction. So my f of x is a fraction and my g of x is also a fraction. So f of g of x is definitely I start with my original f function, and everywhere I see an x, I'm going to put my g. So that's why I've substituted in 1 over x for this, because 1 over x is my g function. This is just really complicated because I've got a fraction divided by something with another fraction, so I'm going to simplify by multiplying times 1. So this is x over x. So this reduces to 1. It doesn't matter what x is. So I'm not changing the value of my function at all. But 4 times x gives me my numerator, which is 4x. But you see, if I multiply and distribute the x on the bottom, 1 over x times x is just 1, which is way simpler. And 2 times x is just 2x. So now I don't have a fraction in a fraction, kind of like, a fraction in a fraction, like Inception, if you want to quote a movie. All right, so my f, or fog of x, is 4x over 1 plus 2x. So that is f composed with g of x, where I have a rational g and f. So let's take a look at the domain. So if I'm taking a look at the domain, remember that it's the intersection where they overlap. So there's nothing weird with these functions that they're both fractions. So they're going to overlap everywhere except for where their denominators equal 0. So I got to find out where g equals 0. Well, that's simple. The domain of g is 1 over x. So what would make x equal 0 is 0. So x can equal 0. So I'm going to say it again. Since my g function is just 1 over x, what would make the denominator equal 0 is if the value of x was 0. That's why x cannot equal 0. So now I'm going to take a look at the whole composite function. And again, I'm going to make sure that where the denominator is, this 1 plus 2x, I want to find out where that equals 0. So I solve for x, and I see that x is equal to 1/2. If the denominator equals 0. So it cannot equal these values. It can equal anything else but 0 and negative 1/2. So again, they overlap everywhere else except for these two, which would make the denominators of the g and the denominators of the composition equal 0. I'm not worried about f because I'm not dealing with f, I'm dealing with the composition of those functions. So I have to deal with g because that's the second function, or what's on the inside. I'm making air quotations that you can't see. And the composite function itself. So those are the only two that I'm really worried about for the domain of the composition f of g, or the domain of fog. So let's take a look at the value of this composite function. I think something got clipped off here, but you see I'm just taking the value, this says 2, so I'm going to plug in 2 for the g of 2. Now g is just 1 over x, so I have 1/2. Awesome, I plugged that into f, and remember f was, it definitely got clipped off. This is 1/2 plus 2. So I have 1/2 plus 2, well that's 2.5. So 4 divided by 2.5, or 4 divided by 2.5 is 1.6. So that is how I get the value of f composed with g of 2, or the fog of 2, just 1.6. Again, I'm taking the value of the answer of the g function when I plug in that 2. And that's it. So there's a lot of meat in this video, and you should definitely take a look back and go over it slowly to make sure you understand each part before doing the homework. But other than that, make sure that you are reviewing these videos as you go and participating in the discussions that I have posted if you're in one of my online classes. But elsewise, that is the combination of functions and composite functions.